So now we will discuss about the Kronig-Penney model. It is an important topic in your syllabus. This usually comes as university question as essays. So treat it as a very important portion. So this model is developed by Kronig and Penney. That's why the name Kronig-Penney model. This model is developed for finding the allowed energy values for conduction electrons in a periodic lattice, and we are treating this model. In this model we are treating a square well periodic potential. Okay, so square well periodic potential is the assumption here. So we can draw our periodically varying potential like this. This is the figure we just explained in the first part. So this is periodically varying potential. Now the Schrodinger equation for free electron is written as for x is equal to 0 and a. For x is equal to 0 and means this region 0 and region, this region the potential is 0, potential is 0. So we can write the Schrodinger equation in this region as d square psi 1 d square plus 2m. Usually here a term comes e minus u. In this region u is 0, so no u term, so 2m e by h cut square into psi 1 is equal to 0. So the wave function in this region, this region is treated as region 1 and this region is treated as region 2. This is a region of 0 potential and this is a region of a positive potential of value u is 0. So that is the difference between region 1 and 2. So for the region 1, the Schrodinger equation is this. So we can written like this: d square psi 1 by dx square plus alpha square psi 1, where alpha square is 2m e by h cut square. You have studied this kind of equation in your quantum mechanics class of 5th semester BSc. So the solution of this equation is of the form psi 1 a e raised to I alpha x plus b e raised to minus I alpha x. This is treated as equation number 1. Now for the region x in between minus b and 0. So for the region 2, here the potential is u0. So the Schrodinger equation will become d square psi 2 by dx square plus 2m by h cut square e minus u0 psi 2 is equal to 0. Okay, so we can write this equation as rearranging the terms. E minus u0 is written as u0 minus e. So a minus sign will come here. So this can be written as minus beta square psi 1, where beta square is equal to 2m h cut square into u0 minus e. And the solution of this equation is of the form psi 2 is equal to c e to the power beta x plus d e to the power minus beta x. You know how this comes, you have already studied this. And the solutions 1 and 2 should be a block function. So these are the wave functions. This is the wave function in region 2. This is equation number 2. And this is the wave function in region 1. This is equation number 1. So the solution of this is, and since this is a periodically varying potential, this wave function should be a block function. That is that it must be of the form psi of x is equal to uk of x and e to the power I kx. Then psi 2, this is the equation psi 2 of a plus b should be uk of a plus b into e to the power ik of a plus b. Okay, I mark it as equation number 2a. So uk of 0 can be e to the power ik of 0 because this is periodically varying in nature. Therefore uk of 0 is equal to uk of a plus b. The potential is periodically varying, so we can write it as uk of 0 and e to the power ik into a plus b. So psi2 of 0. Psi2 of 0 can be written as psi2 of 0 is, this equation comes by putting a plus b is equal to 0 in this equation. So this will become psi2 of 0 as uk of 0. So we can, so the uk of 0 now becomes psi2 of 0. So this equation can be written as psi2 of a plus b into psi2 of 0 instead of uk of 0, psi2 of 0 into e to the power I k into a plus b. Similarly, psi2 of a can be written as psi2 of minus b into e to the power I k into a plus b. I have explained this here. You just go through this. This is the steps for this equation. This is a similar mathematical, not mathematical, this is purely mathematical, and we have explained how this equation comes. So you just go through this and we will get this equation. Okay, now psi and d psi by dx should be continuous at the boundaries at x is equal to 0 and x is equal to m. So the condition, the wave function should be continuous at the boundaries. So at x is equal to 0, x is equal to 0, a plus b is equal to c plus d. That is, these are the two wave functions. The equation 1 and 2 are the two wave functions at the 2 region. So this should be, these wave functions should be continuous, and so at x is equal to 0 and x is equal to a. So at x is equal to 0, if we are equating these two equations, we will get a plus b is equal to c plus d. A plus b is equal to c plus d, and I alpha into a minus b is equal to beta into c minus d. And at x is equal to a, here it is, here at x is equal to a, if you are equating this equation, we will get the form, this, we will get these equations. Okay, now so these two equations, you may be confusing by these two equations. This is the condition psi of psi 1 of x is equal to 0, that is equal to psi 2 of x is equal to 0. This is the condition for wave function to be continuous at x is equal to 0 and it is equal to 0. And this is d psi 1 by dx. This also should be continuous at x is equal to 0 and d psi 2 of x is equal to 0. These are the two equations. So for the wave function to be conditioned, these two conditions should be satisfied. This, that is, psi and the derivative should be equal at the bound at x is equal to 0 and x is equal to L. So these are the at x is equal to 0 condition, and at x is equal to is 0, x is equal to 0, sorry, x is equal to a, this is the condition psi 1 of x at a is equal to psi 2 of at x is equal to a. This is this equation, and this equation represents psi 1 of d psi 1 of dx at x is equal to a, and d psi 2 of d psi 2 by dx at x is equal to a. These are these four equations. So now we have got four linear equations which will have a solution if the determinant of the coefficients of a, b, c and d vanishes. So we have got four equations, and it will have a solution when the determinant of the coefficients vanishes. So if we are writing down the coefficients in the form of determinants and find the determinants, we will get an equation like this. We can you can write the steps if you want. I haven't written it here. So after checking this condition of determinant to be 0, we will get this equation, beta square minus alpha square by 2 alpha beta into etc etc. This is equal to cos k into a plus b. This equation is the condition for the determinants of these four linear equations to be have a solution or to be 0, the determinant to be 0. So let's approximate the potential to a periodic delta function. So we have assumed a periodically varying potential. We are approximating here it is a periodically varying delta function. This is obtained when b is equal to when b tends to 0 and u0 tends to infinity. u0 b remains, that is the nature of the periodic delta function is when this width, this is the width b, and this tends to 0, this will naturally shoot out if it is of the nature of delta function, delta function. So we are approximating this periodic function as periodic potential as a delta function, so that when b tends to 0, u0 tends to infinity. So we are treating this potential as a Dirac delta function where u0b remains finite, which implies if we are applying this condition in this equation, we will get sin h beta approximately beta into b, because sorry, not in this equation, we are treating the terms separately, and we'll put back this into this equation. So what will happen when b tends to 0 for sine function? As b tends to 0, this value, this angle will be very small. So for small angle, this will be tends to sine theta. For theta, small theta will be theta. So this is beta into b, and cos theta tends to 1 when beta tends to 0. And what is b square minus alpha square? B square minus alpha square become, this is the b square minus alpha square term, and this will become approximately 2m by h cut square into u0, because comparing to e, u0 is shoot out to infinite value when b tends to 0. So this difference is very negligible since u0 is infinitely large compared to e. So we can neglect this term, so there will be approximately this. Now substituting this value in equation number 8, we'll get beta square minus alpha square here as 2m by h cut square u0. So we will get, we are substituting this 2m 0 by h cut square to alpha beta etc etc, this form. You just substitute. I have to switch between these two pages. So we have found out each term by putting the condition b tends to 0. So substituting this equation back into 8 will give you this equation. Okay. Now what we have done is arrangement of terms here. Here we have taken this term to alpha to alpha here in the first term. So sin alpha a by alpha a. Sorry, this is not 2 alpha, this is alpha into a. This is my mistake by written, this is alpha into a. Sorry. Let me just check it. Yes, this is alpha a. This is alpha a. So this is alpha m. Now we are substituting this mu0 ab by h cut square as p. This is defined as the scattering power of the potential barrier. It is a measure of the strength of u0 in b. This is defined as scattering power of the potential barrier. Now this equation will be reduced to the form p sin alpha by alpha a plus cos alpha a by cos ka. here note the point that here in the left side this is a function of variable alpha a, but in the right side it's a function of k into a. So this type of equation is known as transcendental equation whose solution can be obtained by plotting LHS against RHS. So LHS is a function of alpha a and RHS is a function of Ka. So the solutions of this kind of equation can be found out by plotting LHS versus RHS. And for certain values of alpha a and Ka, the curve will intersect and the above equation is satisfied at the points of intersection. So if you are plotting the graph between LHS and RHS, at some points this curve will intersect and the point of intersection will give you the solutions of this equation. Those values of alpha and K for which the curves intersect give the allowed energy values and the wave vectors. So that values will give you the allowed energy values. Alpha is related to energy as we have seen from this previous equation. So we are going to plot this function as LHS versus RHS, and we will find out the solutions and hence the allowed energy values. So consider a plot of LHS. LHS means alpha A for a value of P is equal to 3 by 2. Here is a factor, a coefficient P appears. So we are plotting this function for P is equal to 3 pi by 2. The allowed energy values of E of the electron are given by those ranges of alpha A for which the function lies between plus or minus 1, because RHS of equation is bounded by plus or minus 1. So right side the term is, so x-axis we have taken alpha A. So the RHS is a function of k into A. So RHS is a function of RHS is a function of k into A. So this is x-axis is Ka. So y-axis we are plotting the LHS for the value P is equal to 3 pi by 2. Now, so what we will get from this equation? So this ranges of alpha are shown by shaded regions in the graph. So we will get a, so for LHS we are putting the values of alpha. This is the LHS function. So what we are doing is we are putting values for alpha A. So as the value of alpha A, this is a combination of sine and cos function, and there is here in the first term there is a factor called P. So that function will appear as this curve. This is the curve of the LHS function. This amplitude varies because of the factor P and the sine function, because it varies as the sine function varies its value when alpha A changes, and plus there is a value of cos alpha, and there is a coefficient also. So the first value will be at 0, will be like this, and this function will appear like this. And what is the graph of right side? Right side function is cos k a plus cos ka. If we are putting values for ka from 0 to any angle, we will get the maximum value of cos function can be switched between plus 1 and +1 and -1. So this is the boundary. This is the boundary determined by the cos function. That is, this value can be, the value of the cos function can vary in between these two boundaries, that is +1 and -1. So I have fixed a boundary for this cos function. So the cos function and this sine, the right side function and left side functions will intersect at these points. So this is the boundary determined by this cos function. So it will intersect at these points. These are the points of intersection. Similarly, on the left side, these are the points of intersection of this LHS and RHS functions. And you can see some region the value of this function lying outside this plus or minus boundary. So these regions are lying outside the boundary. These are lying outside the boundary, and these regions are also lying outside the boundary, because if these two this equation will have a solution whenever these two functions intersects, and then it will have a common solution. So the point of intersections are this. So this is the RHS boundary, and this is the LHS boundaries. So the point of intersections will be this. So only at this point it will have a solution. The regions outside this boundary does not represent the solutions of this equation. So these regions are not allowed, or only these regions, this intersection, these regions are allowed energy levels, and this will give you allowed energy level values. And the regions, these regions are that region lying outside the boundaries, these regions. So the region from here to here and the region from here to here are, that is for this region, and similarly for left side, the region lying here to here are outside the boundary, and region here to here are outside the boundary. So these regions are forbidden regions, and only region lying this come inside the boundary, and this region, these are allowed energy. So this range will represent the allowed energy range values, and outside boundary values are regions are forbidden regions. Okay. So this is how we are finding out the energy, possible energy values. So there are forbidden regions or energy gaps in the possible energy values of the conduction electrons. This occurs at alpha A is equal to plus or minus n pi. So you can see this outside region occurs at minus pi, 2 pi, pi value, 2 pi value, 3 pi value, etc. So for alpha A plus or minus n pi, the conduction, the regions will be forbidden region. Okay, so for alpha is equal to plus or minus n pi, LHS is equal to plus or minus 1. You can find out, you will get this from this equation. LHS will be plus or minus 1. This cos, which means cos Ka is equal to plus or minus 1. That is, LHS equal to plus or minus 1a means, which is equal to RHS. RHS is cos Ka, so that will equal to plus or minus 1, which implies Ka is equal to plus or minus n pi. So this value will give you the forbidden energy region. At these points, forbidden energy regions occurs. K is equal to plus or minus n into pi by a. So let's plot the function of graph of E versus K. So the K values I marked here. So plus pi by a, 2 pi by a, 3 pi by a, etc. and negative values at the left side. So at plus pi by a, plus 2 pi by a, and plus 3 pi by values, forbidden regions occurs. So this can be drawn like this. So These are allowed energy values. These are energy. What will happen here? These are forbidden. At it plus 2 by a, these are a forbidden region. So a energy gap, and and another energy gap occurs at plus 2 by a plus 3 pi by a, etc. So this graph can be drawn like this. So this region are the allowed energy levels. This represents forbidden region, and again these energy levels are allowed, these are forbidden, etc. So the discontinuities in the energy spectrum occur at brilliant zone boundaries. You haven't studied brilliant zone boundaries, I think. This is in your first module. This is the this can be explained using the reciprocal lattice vectors. So brilliant zone boundary can be defined as the Wigner-Seed cell boundary in the reciprocal lattice. You know what is Wigner-Seed cells? Wigner-Seed cells is the boundaries covered by the perpendicular to the bisectors of the nearest neighbors from a point. So I will tell you. So if you have a crystal system like this, we are considering a point, any point, and what we are doing is we are drawing vectors to next nearest neighbors, and we draw perpendiculars to this perpendicular bisectors of these vectors, and the boundary generated by these perpendicular bisectors will be Wigner-Seed cell. And this Wigner-Seed cell in reciprocal lattice is known as brilliant zone boundaries. So this discontinuities occurs at the brilliant zone boundaries. Thus, energy bands and energy gaps in the allowed energy values for conduction electrons is a consequences of the periodic potential of the lattice. So we have started from the assumption of a periodic varying potential developed by Kronig-Penney, and we have arrived at the conclusion that this band gap originates because of this periodic nature of this potential. Remember from the beginning itself, what we have done from the beginning, we have assumed a periodic potential system, and we have drawn this periodic potential figure, and we have write down the Schrodinger equation for the separate region of potential having zero value and potential having large value, and we have done all this, and what we have got at the end is energy values, allowed energy values and forbidden energy values. So this energy gap occurs due to this periodically varying potential. Okay, so this is Kronig-Penney model, and this explains how the energy bands originates in such system. So now we will discuss some features of this model. So at alpha is equal to plus or minus n pi, from this equation 9 is this. So alpha a is equal to plus or minus 1. Alpha a is equal to plus or minus n pi. We will get left side sign function will vanish, left side cos alpha. So that will equal to cos Ka. This implies Ka is equal to alpha A, which is equal to plus or minus n pi. So K is equal to plus or minus n pi by A, or n is equal to 1, 2, 3, etc. These values of K are points of discontinuities in the energy versus K graph for electrons in the crystal. These are the Brillouin zone boundaries. Okay. Now, as the value of alpha A increases, alpha A is the variable of the functions at the left side, the width of the allowed energy bands also increases and the width of the forbidden bands decreases. This is a consequence of the fact that the first term P sin alpha by alpha A decreases with increasing alpha A. Because in the first term there are two terms, one term with the sine function and the second term with the cos function. But in the first function there is an additional coefficient called P. So as the alpha A value increases, this sine function and cos function value will, the sine function value will increase because sine function can vary from 0 to 90 to the maximum value. So as alpha increases, sine function value increases, but the cos function value may decrease, but there is a factor in the denominator alpha A. So as the value of alpha increases, allowed energy bands also increases. So the width of the allowed energy bands increases due to this factor, but as the forbidden energy bands decreases. Okay. Now the third point is, as P increases, the width of the energy bands decreases and that of the forbidden energy gaps increases when P tends to infinity. The allowed bands reduces to discrete energy levels. So as the value of P increases, the width of the energy bands decreases. So if P tends to infinity, the energy bands reduces to energy levels. Instead of bands, it will reduce to energy bands. You have noticed the width, the varying width of this energy bands here. This is my mistake of drawing. Here the width of this energy bands, this allowed energy bands is increasing actually. Allowed energy bands is increasing actually. I have shown it in the left side correctly. Here the width of the allowed energy bands is increasing and that of the forbidden gap decreases. Here it is shown. Here, yes, this allowed energy bands is increasing as the value of alpha A increases. Okay, and it varies according to the values of P also. So when P tends to infinity, what will happen? Sine alpha terms, the first term will tends to 0 because infinity in the first term, so sine alpha terms will be 0, but alpha A not equal to 0. So alpha A can be plus or minus n pi. So alpha square is equal to n square pi square by a square. Alpha square is 2me by h cut square. So that we will get energy as n square h cut square by 8m a square. So the energy levels are, we are getting the energy levels like this, 4n is equal to 1, 2, 3, etc. So this will happen when P tends to infinity. So this happens like this. Okay, these are the available energy values for an infinite square well potential as obtained in the free electron theory. Okay, now the nature of the potential well and boundary when P tends to infinity. So P tends to infinity means, what is P? So P is mu0 a into b by h cut square. So P tends to infinity means P is equal to m u0 a b by h cut square. So when P tends to infinity means u0 into b tends to infinity. So that implies b tends to infinity. That is, the width tends to width of the potential region is going to infinity. So consider the situation when b tends to infinity. B tends to, this is our normal function. When b tends to infinity means this width, this is the width of b. B tends to infinity means this is infinitely large, means this will be like a constant potential. That is, this width b is infinitely large compared to a. So this potential, this periodically varying potential will be like this, will become like this, u0. So now there is a constant potential u0 inside the lattice. By the change of the reference value, we can redefine as zero potential. We can redefine this zero potential instead of a constant potential inside the lattice and an infinite potential outside. The lattice is the situation of an infinite square well potential then. So by changing the reference value, this u0 can be taken as zero potential inside and infinite potential outside. So this will be like an infinite square well potential problem. Now the next case is when P tends to 0. When P tends to 0, the energy bands overlap into a single band and the forbidden bands vanishes. That is, when P tends to 0, from our equation, we will get cos alpha is equal to cos Ka, because the sine function with coefficient P tends to with the coefficients P will become 0 and P tends to 0. So on the left side cos alpha A, right side cos Ka. So alpha is equal to K, alpha square K square. So we will get from this E is equal to h cut square K square by 2m. These are the continuous energy values of a completely free electron. So in the E versus K graph, the parabolic curve drawn in dashed lines represents these energy values. So I have shown figure as parabolic curve in the E versus K graph. This is parabolic curve representing the allowed energy values. These are the energy values represented by this equation. Now the nature of the potential well and boundary when P tends to 0. So what will be the nature of the potential? P tends to 0 means u0 B tends to 0, which implies B tends to 0. B tends to 0. So this is our periodic potential. When B tends to 0, B tends to 0 means the width is this is the width B, this is B, and this is A. So this is shrinking. This width is shrinking to 0, which implies this width is just like a line. The width is, this is B equal to 0, that is width is reduced to 0, these points. So what will happen? By the change of the reference value, that is a single valued potentials at these points when B tends to 0, u0 at this point, etc. So by change of reference value, u0 can be redefined again as 0 when redefined as 0. When u tends to 0, the electrons experience 0 potential in an infinite lattice. That is, they are completely free. Hence, their energy values are continuous. So, potential zero means the electrons are completely free inside the lattice. That is, hence their energy values are continuous. So, no energy levels. They are if they are continuous, that means the electrons are completely free to move inside the crystal lattice. But energy levels occurs when there is a potential which is periodically varying of nature. So These are about Kronig-Penney model and the and how this model uh, explains the origin of energy levels, energy bands, and energy bands in solids, and how the forbidden energy gap arises. So this energy bands, origin of energy bands, whether it is an allowed energy bands or forbidden energy bands, are the consequences of the periodically varying nature of the potential inside the crystal system. So we have found the we have discussed the features of this model. Okay.